Let me start by thanking very warmly the organizers for the nice workshop and for this invitation. I'm going to present some results I obtained on the Zeta solutions. Here, a paper with Johan Blobeck, who is in the audience, and another paper here. This was before the Swampland Criterion, and this was after the Swampland Criterion. All right, but I will start slowly and put things a bit into context. And so I think the appropriate context is cosmology. And so we all know that there's been, in the last decade, very important observations in cosmology by Planck, and also Bicep 2 and Keck-Array and others, which have set important constraints on the cosmological models. And there will be more to come, but despite this, there are still quite some models which remain and which are in good agreement with the observations. And therefore, for us as theorists, we may wonder, are there any theoretical constraints that we could bring in and help us distinguish in the various models? And an important requirement that we could put on the models is whether they can be derived or whether they're compatible with a fundamental theory or a quantum gravity theory, which is important for cosmology. Or say more fashion of this question is the cosmological model in the Swamplands, which means it cannot be derived from quantum gravity, or whether it's not in the Swamplands. This question is actually related to a question of having de Sitter solutions derived from quantum gravity. And the reason is the following. By solutions, I mean a solution to where the four-dimensional spacetime is a de Sitter spacetime. The reason is that, say, the mainstream models, or say some simple models which do exhibit de Sitter. So I think we all know that for instance, the present attracted in the few words, according to the model we have now is attracted to a pure de Sitter spacetime, where the cosmological constant would dominate everything. That's the first example. And then in the early universe, if we consider inflation, so here I depicted for a single field inflation with the inflation phase here. After the inflation, there's a point here, which is a minimum of the potential, and it's also typically considered to be a minimum, and this type of vacuum minimum is required for reheating to occur. This is an important point, actually, after inflation. So this is also a de Sitter solution, and the inflation phase itself is very close to being a de Sitter solution. Right, so we see there are always stable or metastable or just slightly unstable de Sitter solutions in these models, and so in that case, the question becomes, can we get de Sitter solutions from quantum gravity? That's where the problem starts, because as we have heard many times, it is actually difficult in string theory to obtain de Sitter in a controlled fashion. It's especially difficult to get a de Sitter vacuum. So by vacuum, I mean minimum of potential or metastable solution. And so if we take this difficulty seriously, there are roughly two options. The first option is that you are more on the cosmological model side with the de Sitter solutions, and the other option is that you're more on the string theory side. This is, of course, very schematic. But so if you follow the first option, you say, I want to keep my models with de Sitter solutions, then it's basically going to be constraining for string theory. This is just one example. In the seminal paper by Silverstein and Westphal on monodrome inflation, there's a simple a mechanism proposed where a brane moves on a twisted torus. And in these papers, we have shown that there's actually no de Sitter solution to end this process, to be this endpoint of inflation. There's actually no solution at all. There's no Minkowski or ADS solution that would do the job. So this is an example where if you impose this criterion, you can constrain the cosmological models, which are built from string theory. But this point can also be seen as a positive thing, in the sense that if it's very constraining for string theory constructions, then maybe there's still a corner, but a very small corner, where you can actually obtain these models. In that sense, it's a bit predictive for string theory. So it's a predictive corner, if you want. Okay, the second option is that it's very hard to do this from string theory, and therefore string theory is telling us something. And it may mean that I actually want to consider different types of cosmological models. And I think, as we have seen in the literature, whether it is quintessence or multi-field inflation or others, typically the cosmological models will be a bit more involved if you want to match the observations. Right. So I think this is the idea behind this the Cedar Swampland Criterion that we've heard a lot about. So let me just quickly state it to not to waste too much time. So this criterion is the following. If you have some 4D theory like that with gravity and scalar fields with a potential, if this theory is not in the swampland, meaning if this theory is the low energy effective theory coming from string theory, then it should obey this inequality here. And as we have seen, this inequality implies that you cannot have a de Sitter solution. You cannot have a de Sitter extremum. Right. So, okay, the conclusion of this little reasoning that I did is, I think that there are several important points. The first point is that this requirement, can this cosmological model be derived from quantum gravity? This is an important requirement. This is very fruitful because it's really constraining. The second point is that I believe that the problem of de Sitter solutions in string theory is actually central in this question. So now the plan of my talk is the following. First, I will make some comments on de Sitter solutions in string theory and the relation to the swampland. And in the second part, I will discuss the constraints on classical de Sitter solutions. All right. So again, we heard a lot about this already, so I will be a bit quick. There's this very nice review by Ulf Danielsen and Thomas van Ritz that I recommend. I think in this whole story of trying to obtain de Sitter from string theory, there is a very important point, which is that there's a distinction to be made between the 10-dimensional level, which can be viewed as the quantum gravity level or string theory level or supergravity level, and the 4-dimensional level, which is the cosmological model of the low-energy effective theory. And I think the complicated interplay between these two levels is the core of the problem, the difficulties that we see. Okay, so to get de Sitter, there are very roughly two types of approaches, and I'm sorry because this is very schematic. There are the approaches that I qualify as loosely as 4D approaches. So these are various approaches in which, I mean, you may start at 10 dimensions and so on, but at some point in the procedure, you include some ingredients at the 4-dimensional level, like a term in the potential, for instance. And immediately you raise the question, how can I obtain this term in the potential, this 4-dimensional ingredient from string theory in a controlled manner? And this is the source of all the discussions. So I want to speed up a bit here, so let me not enter the details. I want to summarize this situation by saying there are constructions in 4 dimensions where they obtain de Sitter solutions, and the question is how do you get this from 10 dimensions? And there's a lot of progress being made on this, and this is work in progress, but I think so far it's not really established. Then there's the more conservative 10-dimensional approach where you look for classical perturbative string backgrounds which have a 4-dimensional de Sitter space. So these are typically 10-dimensional supergravity solutions with D-branes and orientifolds. Here, in comparison to the previous thing, you have a good control and good realization in string theory. But the problem here is not this. The problem is actually to find solutions. So here it's very difficult to find de Sitter solutions and even stable ones, so that's hence the picture here. In more detail, so let me enter a bit the details. There is no such solution in Hedge-Hartog string. And in type 2A and type 2B, finding such solution is not excluded, but it's very constrained, and I will spend the second part of the talk on this. But I would like to emphasize a point here, which is that the difficulty is not a technical difficulty. I mean, it is technically difficult to find the zeta solutions, but the theory doesn't like it. It's intrinsically difficult to find the zeta solutions. And I like to illustrate this point by this formula here that we obtained with Joan in this paper, and also with Thomas van Riet in another paper. So this expression is derived by considering 10-dimensional supergravity with parallel D6 and O6, and you just combine the equations of motion in order to get an expression for the 4-dimensional Ricci scalar or cosmological constants. And it looks complicated, but actually it has a very simple pattern, and you can see that the first 3 lines are actually all negative, because it's minus squares. So the first 3 lines are completely negative or 0, and if you want to get the zeta, there's only the last line which is left. And so the last line is a combination of very specific components of the H-flux and some specific curvatures in your internal manifolds. So if you want to get the zeta, you see that it's intrinsically difficult, because you should get this last line, this combination of fields non-zero, positive, and balancing the rest. So that's an illustration of this idea. Right, last but not least, I think there's an important point which has been raised a bit, but not so much, which is there could be difficulties to go to 4 dimensions. Because after all, this whole Swampland discussion is about low energy effective theories. And so one could have problems performing a low energy truncation and reaching a low energy effective theory. And this is a very important point. So suppose you actually get the zeta solutions in 10 dimensions, then you want to do a low energy truncation and obtain an effective theory. And so it turns out that there exists some 10-dimensional de Sitter solutions on group manifolds. I will come back to them. Among the various group manifolds which exist, some group manifolds are nil manifolds, but no solution has been found on nil manifolds. I, however, presented an argument saying that it's only on nil manifolds that you could obtain a good low-energy truncation. So in other words, on the other group manifolds, or in the de Sitter solutions which have been found, which are on other group manifolds, you always have scales, energy scales, which are higher than the Kaluza-Klein scale. Which means that when you want to truncate to low energy, you're going to have difficulties, because you typically want to truncate below the Kaluza-Klein scale. So if you insist on truncating and going to low energy, you will basically kill the solution. That's my conclusion. So maybe, in other words, maybe the de Sitter solutions you find are at 10D and have too high energies, and you cannot find them in 4D. So it's another perspective on this Swampland criterion which could be interesting. I think we met this idea of the low energy and the cutoff and so on in various discussions already in the talk by Arthur Ebecker and the comment on Joe Conlon's paper, and in Ralph Blumenhagen's talk also. Anyway, the 3 points I mentioned, so the difficulties to lift the 4D solutions, the difficulties to find de Sitter solutions in 10D, and the difficulty to go to 4D after all, are all in favor of this de Sitter Swampland criterion. But now, of course, we should start checking the details. And, well, the first big detail is that there exists classical de Sitter solutions in 10D, right? So they have been obtained by these people here on group manifolds with intersecting orientifolds. So as Tim Fraser has explained in his talk, there could be various criticism on these solutions. So you may doubt on their validity. You may hope to find other solutions which do not have this problem also. I don't want to enter this. I want to make the following remark, which is that all these solutions have been shown to be unstable. So in the sense of being tachyonic or having a scalar field at a maximum. So the good statement is actually that there is no known classical de Sitter vacuum. So this means that maybe stability is actually a key point in this discussion. And so this is the reason why I proposed to refine the de Sitter Swampland criterion by this expression here. And so I propose that if your theory is not in the swampland, but there exists some constants B and C such that you have such a linear combination of the potential, the first derivative, and the second derivative, which is negative. Indeed, on an extremum, the first derivative term vanishes, and so you are left with this. And this implies that you cannot have stable de Sitter solutions, but you can still have tachyonic de Sitter solutions, or unstable de Sitter solutions. So you may rewrite this formula in various manners. The reason I decided to present it this way is that you don't need to include all scalar fields. If you have just one tachyon, it's actually enough to say that it is unstable. So that's why I prefer to sum on the fields like that. But I'm certainly happy to rewrite it, for instance, by replacing the first derivative by a gradient. So actually, if you do this and you focus simply on single fields, then you can rewrite this as this expression here in terms of epsilon and eta, the slow-roll parameters. So this formula will appear in the revised version in the next days. Anyway, this is simple enough, and it could be, I think, checked, and the constant could be a bit computed on various examples, and cosmological implications could be studied. Okay, I think at this stage we've made very interesting general statements, but now we definitely need more analytical results. We need to try to prove or disprove these things in general. And so maybe less example-based, but more analytical results. And so that's why I want to turn now to the constraints on 10-dimensional classical de Sitter solutions. So I'm coming back to the second point I presented, these 10-dimensional classical de Sitter solutions. I'm gonna review and present new constraints on those. And right. Okay. So all I'm gonna say is present in the introduction of my last paper. So in case you can find it there. So to obtain constraints on classical de Sitter solutions, the reasoning is very simple. You take the equations you have to solve, you combine them in some manner, and you get constraints. So for instance, you get the expression I showed you for R4. You impose this has to be positive, and you deduce some constraints. So to do this, you can do this in two manners. Either you take the 10-dimensional equations of motion and you mix them, or you take the 4-dimensional potential and you study the extrema. And as Tim Braze has reminded us already, there's a popular approach in the 4D way, which takes this potential of two scalar fields, rho and tau. And so in this way, you obtain three equations. You obtain the two equations for the extrema, and the Einstein equation gives you a condition here. So you can actually show that this is equivalent to taking the integral of some 10-dimensional equations of motion, the trace of the Einstein equation along various directions, and the 10-dimensional dilaton equation of motion. Anyway, long story short, you have three equations, so you just start combining them and you get some constraints. You get constraints on the existence of solutions. You may get some no-go theorems or identify some ingredients which are necessary. And so you end up with a table that we have seen already in some talks, which is the following. Here obtained in 4 dimensions and here obtained in 10 dimensions. So the de Sitter solution requires T10 to be positive. This is the source term, so this means you essentially need orientifolds. And then you have various options. You can have a positive internal curvature or negative internal curvature. And then the situation depends on the size of the source, so you consider parallel sources. So here in this table, an empty box is a no-go theorem. So you cannot have de Sitter solutions in all these boxes. And in the case there's something written, then it means you need these ingredients. Right, so I think this is the table we have seen. And from now on, I will show you more constraints and update this table. So an extra constraint you can put is simply considering extra equations. And so the first equation to consider is the 10-dimensional source Bianchi identity. So this equation here with a source term here. And from this you deduce more constraints and more ingredients. So the first important step is that with this additional equation you can actually show that there cannot be de Sitter solution with P equal 3. So you just erase this line. And for the other cases, you actually deduce that you need more ingredients. And these are the ingredients. So you need some combination of fields, which is the one I showed you previously in this expression. And you need this F. This F is like a specific spin connection component. So you need this specific spin connection component with index along the source, parallel to the source, and over this is transverse to the source. On a group manifold, this is a structure constant with some specific indices. Then you can play the same game with intersecting sources, and it turns out that in that case it is less constraining. There are a few ingredients which disappear from this table, and so this may explain why some solutions have been found with intersecting sources, but not with parallel sources. Right, so all these results were known, and now I'm going to present some new results that I obtained in my last paper. So I copy the same table as before, and we're going to work more on it. So the first thing is that you can do a little rezoning in the case of p equals 4. So in that case, you can consider yet an additional Bianchi identity, this one here. And so for p equals 4, this is df0 equals 0. This means that f0 is constant, so the Roman's mass is constant, but it has to be odd under the orientifold projection, so it imposes that f0 has to be 0 for p equals 4. However, f0 is a necessary ingredient here to get the sitter, and here it's an optional ingredient. So f0 is 0, so then you actually have to erase all these options. And you are left just with this, and so in particular, you are left with only the possibility of having negatively curved manifolds, which is interesting. Right, let's go further. So in my last paper, I actually introduced a new scalar field, sigma, which was proposed in that paper already. And sigma is a fluctuation of the internal metric, but contrary to the volume, sigma distinguishes between the directions parallel to the source and transverse to the source. So from this, you get new constraint through this new extremum equation, and from a Tandy perspective, this is the same as the trace of the Einstein equation along the parallel directions. It turns out that with Johan, we actually considered this equation in 10 dimensions, and we obtained some constraint from this, but here we'll also obtain new ones. And so the constraint is that, in particular, you need some extra ingredient here, a different type of structure constant on group manifolds. Right, so just to show you some formula, this is the potential in terms of a free scalar field, rho, tau, and sigma. And you see the dependence, and you see the various 10-dimensional background values of the supergravity fields. This is the expression for the 6-dimensional curvature that you have to separate along transverse and parallel directions, so there's various dependence on sigma. Right, and so you start playing with this. And from this, I obtained these new constraints by focusing on group manifolds. So this is simpler, but this is also the context where solutions have been found. And so I obtained some constraint in terms of a parameter lambda, which is simply a ratio of some specific structure constant. It's just a convenient parameter. And so I showed that there is no classical de Sitter solution with parallel sources if lambda is negative or if lambda is bigger than 1. So you take these values and you go back to the structure constant, and so you can deduce what it means in terms of the algebra of a group manifold. And so what it means is that there's actually no de Sitter solution on nil manifolds, on group manifolds with semi-simple groups, and on some solved manifolds. So there's only a very small set of group manifolds which is left. Right, and this is for parallel sources. Okay. So, ideally, if you want to support the de Sitter Swampland criterion, you would have liked to obtain a full no-go theorem here. And, well, I did not manage to do this. So there is indeed a small region of lambda between 0 and 1, which is left, for which I cannot conclude. Another way to say it is that there is still the possibility of finding the de Sitter solution with parallel sources in this region. And to my surprise, I actually obtained more. I actually found some stability island in this small region. I showed that there's even a smaller region here with these parameters, where if you have a de Sitter solution, the free scalar field would have a second derivative which is positive. This was completely unexpected to me because there is a paper, the paper where they introduced sigma, they actually argue that the systematic tachyon which is seen in this solution should be among these three scalar fields, ρ2 and sigma. So I didn't expect to find any stability region. But here I'm working with parallel sources, so maybe it's a bit different than their case. I don't know. In any case, there remains this tiny region of parameter space where it's still possible to find stable de Sitter solution with parallel sources. So we should definitely explore this, either constrain it more or actually find solutions. I had a remark on the Bianchi identity and the Swampland, but I will skip this. I'll let you check the slides if you're interested. And I will simply summarize. So I expressed this question, which is what cosmological model is or is not in the Swampland, and I argued that I think this is related to, can we get in a controlled manner de Sitter vector from string theory? And so from this point you reach the de Sitter Swampland criterion, and maybe you want to refine this with the stability question, right? And from there, I started a more detailed study to check these ideas, and I presented to you the constraints which exist on classical 10-dimensional de Sitter solutions. And as a conclusion, I think we should definitely explore the stability island for the parallel sources. And we should also explore analytically more the intersecting sources to understand what is happening there. Finally, a point that I briefly mentioned, I didn't have time to develop, is that I think we should really also think about this dimensional reduction question and the low energy truncation versus consistent truncation in this Swampland context. Thank you for your attention.
Thanks, very nice talk. So I have a question about your refined conjecture. For one field, I understand your criteria. For many fields, I did not understand the formulation. Could you rewrite it?
Right.
Or show me, because I don't understand how you can formulate it with the metric in this story.
Right, so...
I don't understand that equation, really. Because if you have a general metric, what does that mean?
Right, so I didn't... In that formulation, I didn't include the field space metric, and I'm happy to have it rewritten with...
No, I don't even know how to do it in that case. So for your next equation, I understand.
Right.
For that one field, I don't have any problem. But for more than one field, I don't know how you write it like that. That's why I always phrase it as two different constraints. You want to combine them, but I don't see the combination.
Okay. I'm just saying that... if you have one tachyonic field, so if there's one maximum in one direction, so the second derivative in that field would be negative, and so you can just pick one C then. You pick one C, this one, which is negative. All the other C's you set to 0, and in that case, you can satisfy this inequality.
Well, so you agree that the black equation does not make sense for general metric, right?
Right, I agree.
So let's talk about the second one. So the second one makes sense to me for one.
Okay.
No problem. Can you write the 2-field or 3-field or n-field version of the second equation? That's what I'm asking.
Okay.
I cannot see how you can write it.
So, okay, fair enough. It won't be equivalent to what I've written, but...
Can you even? Because the only way I can phrase it, or the way I understood, for example, Bargarg and Krishna, and the way I interpreted what you wanted to do was, if there is a unstable direction, then, and if their slope, second derivative is sufficiently small in that direction, then that's one possibility. Or if that's not the case, then epsilon is bigger than some constant. So that I understand as a criteria. To combine them into one equation, I did not.
So maybe one way to rewrite it with the metric would be, for the first derivative, you put your gradient. For the second derivative, you write the Laplacian. maybe.
The Laplacian.
The Laplacian on the moduli space, yeah.
Well, the Laplacian on the moduli space. So wait a second. If it's all these massive modes,
Right.
if you add them up, I bet it's going to be positive always.
Yeah, that's true. That's true, actually. Yeah, that's why. Yeah, that's true. Well, that's why I prefer to write it this way, because I allow the sys to be 0. Yeah.
No, I'm just saying that equation. You agree that it's not generally well defined.
Right.
So
Right.
we are not talking about the black version, because that doesn't make sense.
Okay.
The second equation does make sense, but that's for one field. I understand
Okay.
it. For multi-field.
Okay. Yeah.
By the way, I think Kumrun means that it's not Diffie invariant, your equation, on the scalar field space, so you cannot just write it. No, the thing I wanted to ask is, first a small comment, I think for you said everything in the column P equal 3 I have to delete, but I think when you do that, you have made an assumption about the charge of the objects you include versus their tension, because there is an example of a classical strongly coupled, unstable de Sitter vacuum with an O3 anti-O3, in case that even is allowed in string theory, I don't know. I'm just remarking, so there is some assumption in these kind of calculations.
Yeah, that's true. I assume BPS objects.
Right, but you see, the moment brains are not calibrated, like in the example of Tim and Renata Kalos, you cannot deduce these inequalities. And that's, like with KKLT, we even have that, right? Brains are not calibrated anymore. And
I'm
that
not
can
sure
be crucial.
if calibration is the same thing as BPS, but okay, we can discuss this.
In this case, it is.
Okay.
And then I had one more question. Yeah, the thing what's confusing a bit is you say the analysis has mainly been 10-dimensional, but if you look at, say, Einstein equations and field equations, and you focus on, say, the trace over the internal dimensions of the Einstein equation and some of the traces over the orientifold directions, then I cannot understand how the analysis is not equal to just the analysis I get from a 4-dimensional treatment where my 3 fields are, as you say, rho, tau, and sigma. In the end, these equations should be equivalent, and that's because these are necessarily consistent truncations for any kind of internal space, right? So I don't see, in that sense, what one can gain from a 10-dimensional analysis that one would not have from a 4D analysis.
Well, I mean, you may... I don't want to assume that the Ricci scalar is constant or that my fluxes are constant. So I'm not assuming this. So
but you don't have to. You don't have to.
That's right. So I need to integrate over the 60.
Sure.
So okay, they're equivalent up to the integration. That's what I said.
But I'm saying you can even get those constraints from the integrated equations of motion.
Well, that's what I just said, no?
Yeah, but that's equal to a 4D treatment. And I know in general there might not be a consistent truncation, but there is one in those 3 directions, and then you should end up with exactly the same constraints, but I think it's easier in an effective potential approach.
I think we agree. I said that the 2 things are equivalent up to integration, and it's the same equations after that. So, yeah.
Thank you. First of all, I think also with comment, I don't really know what this equation epsilon eta means if you have a 2-dimensional space, because are you saying that anywhere in field space, eta can never be bigger than epsilon, but in what direction? Let's say eta is positive and epsilon is positive definite, you said, so.
Sorry, you say with 2 fields, you said, or?
Yeah, just generally in field space, as you move around, how do you define eta and epsilon?
No, so this is for single fields.
Which fields?
So this equation becomes this one if you have 1 field. That's what I'm saying. So
this only applies if you have all the fields very massive? And just
no,
one, I'm just trying to understand what is the formulation.
Sorry, you don't understand what?
I'm trying to understand what the formulation of the... Because the equation in the black would kind of make sense if you wrote down invariants under diffeomorphisms in field space.
Right. No, but I think
something like that would make sense. Then you don't single out any particular field. But then Okay, that doesn't. So you didn't do that, but on the bottom one, you single out a particular field. I just want to know which field that is.
Oh, right. So no, I'm not singling out one field. I'm just saying if there's only one field in this equation. So I'm just considering a single field cosmological model. That's all. So if there's no index here, but there's just one field, that's just what I'm saying.
Okay.
In general, I think I agree with all your comment, but it's actually indeed hard to write this in a diffeomorphism invariant manner.
Another question was, so has anybody looked at so if you do consistent truncation, then there's all the other modes that are generically lighter than the modes that you keep.
Yes.
And in principle, you can study them. Like if it's in a sphere, you can look at all kinds of deformations of the sphere. And like people did this back in 70s or whatever when they studied like Duff Nielsen Pope and things like this. Has anybody looked at those kind of directions? Because even if you did find any consistent truncation, what you might call a de Sitter vacuum, that's still no proof because there's all the other modes that are.
Yeah, that's absolutely true. So even if you could indeed, I'm just repeating what you said. Even if with a 40 gauge supergravity, which is a consistent truncation, you would find that all modes are stabilized, which is not the case so far, except maybe in Tim's example yesterday. But even in that case, you are right that one should study the other modes which are not captured by this consistent truncation. I don't have references in mind right now, but I'm stressing that this is an important problem in this business. Yes.
Okay, thank you.
This is more like a comment to the equation where you want to introduce the second derivative also into the Swampland conjecture. I would think that the most natural thing to do if you would like to have second derivative as well is just to think like in inflation with a small epsilon and small eta. And if you have several different moduli, what you need to do is to make sure that you are following the field in the slow roll direction, and then you project the second derivatives in that direction, and then you can see, can I find something which is slow roll over more than a few e-foldings? And that is something that we try to check in this classical theory some years ago, and you couldn't find anything. But such kind of constraints when you look at, you really have to make a difference between different second derivatives, whether they are in the direction of the motion or transverse to it. That but you can do.
This projection is more in the spirit of what I wrote here, because I can indeed take all the C's to 0 except one, and so focus on one field and one second derivative.
Yeah, but I think it makes more sense to separate the two equations into two different.
Oh, I see. Okay, ones. I see. Yeah. Okay.
I think separating makes a lot more sense because the slow roll direction doesn't generally make sense. If you're at the top of the unstable one, there's no stable direction. There's no slower direction, so there's no formulation like that.
No, you have to go a little bit off.
Yeah, I know. So
and then talk about the slow roll, then you can do it.
So there cannot be generally that equation will be ill-defined.